Right, let's take a look at these differentiation questions then. So question 1, add a bit of light. Curve is a parametric equations. X equals sine theta and y equals cos squared theta. Now, although we tend to write cos squared theta like that, it's easier to spot what sort of differentiation you need to apply if you write it like that. It means exactly the same thing. It's cos theta times cos theta. And when we differentiate parametric equations, what we do is we differentiate each part of it. So we'll be doing dx d theta for that, dy d theta for that, and then to get dy dx we end up doing dy d theta times d theta dx to combine it. So that's how we go about doing this. So first of all, we'll differentiate dx d theta, which is just a straightforward standard result. You differentiate sine, you get cos. On the sheet I've given you, I've written it as sine ax, because if that was sine 2x or sine 3x, then when you differentiate it, it basically becomes 2 cos 2x or 3 cos 3x, so long as that's a constant. So sine ax is a cos ax. Well, for us a is 1, so it's just going to be cos theta. And then for dy d theta, what we have here is a chain rule. We've got the function embedded inside the other function. So when we were practicing these, it was the cover-up method that we were using, but the full method is there. So what I'll do for the sake of this example is I'll do it both ways. Okay, so it's going to be chain rule. So it's a good idea to tell the examiner how you're going to differentiate it. So we're going to use the chain rule. So if we're using the one off my supporting formula sheet, then we're going to let u equal g of x. So u is going to be the embedded function. So we let u equal cos theta, and that means y then is in terms of u. So the y, instead of being cos theta all squared, will now be u squared. So we've broken it down into two easier things to differentiate. du d theta in this case will be minus sine theta, and then we're going to do dy du, which will be 2u. And once we've performed that differentiation, we can then substitute back in what we've let u equal. So that's going to be 2 cos theta. And then dy d theta, which is what we're looking for, is going to be dy du times du d theta. So if you remember when we were doing all this chain rule stuff, I was saying, well, that means that the u's would cancel and you'd end up with dy over d theta, which is the same as that side. So dy d theta would be dy du, which is 2 cos theta, multiplied by du d theta, which is minus sine theta. And that's not a subtraction then, that's a multiplication. So you've got minus 2 sine theta cos theta. So when you differentiate cos squared theta, you get minus 2 sine theta cos theta. If you did that using the cover-up method, which we could have done straight away, it's going to be dy d finger, which is 2 finger, which is going to be 2 cos theta, which is that bit of it, multiplied by the differential of what you covered up, which is going to be what you get when you differentiate cos, which is minus sine, which gives you the other bit. So either way, you're going to end up with dx d theta is cos theta, and that should be dy d theta, not d theta d theta. So dy d theta is minus 2 cos sine theta cos theta. Now, you should be able to spot from the trig identities that you've been hammering away at all year that that's the same as sine 2 theta. So you should recognize that you can write that as sine 2 theta. Ultimately, it won't matter if you leave it like that or like that when it comes to answering the rest of this question. So I've got my dx d theta, I've got my dy d theta. What I now need is dy dx. So dy dx is dy d theta, which is minus sine 2 theta. Actually, it might be easier to leave it like that because we're going to have a cos which will cancel. So let's leave it so that's the dy d theta, and then we've got times that by d theta dx. Well, I've got dx d theta, so I need to invert that, which gives me that, and then, as I just spotted, the causes will cancel, so dy dx is minus 2 sine theta. So where are we progressing? So we've got a curve with parametric equations. Show that the equation of the normal to the curve at the point P where theta is pi by 6 is that. So I've automatically gone into the dy dx without actually explaining why we have to do that. We have to do that because when we're finding tangents and normals, we need gradient. We need to use y minus y1 equals mx minus x1. Now we're interested at the point P where theta equals pi over 6. Now I want the normal. So the normal is minus 1 over the gradient of the tangent. If I just put theta as pi over 6 into that, that gives me the gradient of the tangent. So the normal would be minus 1 over that. So when theta equals pi by 6, I need the x and y coordinate of P. The x and y coordinate of P are given by the two parametric equations that we started, the ones you were given with. So P would be the point x sine theta and y cos theta all squared. So if we now put into our calculator, make sure you're in radians, and if you can't remember how to sort that out, you go to, not menu, you go to setup, so shift, setup, angle unit 2, and you're in radians. Then I'm going to save pi by 6 into my x variable. So if I want to work out what sine of theta is, that's going to be sine of x, which is 0.5, and then cos x, work out what it is, and then square it, and you get 3/4 or 0.75. So those are my x1, y1. So now for my gradient, so dy dx will be minus 2 sine theta, which is going to be minus 2 sine x. So that's going to be negative 1. So therefore, m norm, because I'm interested in the normal, is going to be minus 1 over that, which basically means it's 1. So you're changing the sign and turning it upside down. So therefore, equation of normal at P would be y minus y1, which I'm going to now write as a fraction, equals m, which is 1, x minus half. And I've written as a fraction because this is a show that question. And I've got to show that if I worked out this correctly when I was making these questions up, I'm going to end up with that. Oh, am I going to end up with that? Let's see. So I've got y minus 3 over 4 equals x minus a half. I'm going to multiply everything by 4 to get rid of the fractions. So that means I got 4y minus 3, because the 4 over 4 will cancel, equals 4x minus 2. So I'm not going to get to show that. I'm going to end up with 4y minus 4x, not 4y, 4x equals, if I take that 3 over, it becomes 3 minus 2, which is 1. So it's 4y minus 4x equals 1, not 4y minus x equals 1. So clearly when I was rushing through this, I multiplied by the 4 and didn't multiply that by 4. So I've gone wrong either when I was working this out or now. You tell me. So that should be, I think, 4y minus 4x equals 1. So that's part A. Part B, find the coordinates of the points of intersection of the curve and the straight line y equals x minus 1. So I've got my curve x equals sine theta, y equals cos squared theta. And I want to find out where the curve crosses with the line y equals x minus 1. So what that basically means is that they've got to be the same points at the same time. So what we do is we substitute those into that equation. So in one, instead of writing y, I can write cos squared theta. Instead of writing x, I can write sine theta minus 1. Now this then kicks into the work you did with Mrs. John with trigonometric identities and equations. I need to get them all in terms of cos or all in terms of sine or something that's common. Now I know that cos squared can be written as 1 minus sine, oops, that looks like a 2 now, 1 minus sine squared theta, because cos squared plus sine squared equals 1. So rearranging that, I can write this cos squared as 1 minus sine squared. Okay, so now I'm looking at possibly a quadratic. Take the negative sine squared over, I get sine squared theta plus sine theta, and then I'm going to get minus 2 equals 0 into my quadratic. Degree 2. So basically my x values are going to be sine. So I got 1, 1, minus 2. So either sine theta equals 1 or sine theta equals minus 2. Well, sine theta can't equal minus 2 because it oscillates between +1 and -1. So there's no solutions to that particular one. I think I got this answer wrong as well, haven't I? Oh, didn't I do well? So I've either gone wrong again here, or I've gone wrong when I was rushing to work my answers out, which I can't lay my hands on at the moment. So, no solutions. So we're interested in the values where sine theta equals 1. And if you think about our sine curve, which goes between 0 and 1, the only value which gives you a value of 1 is pi by 2. So theta equals pi by 2. Right, let's go back to the question. Find the coordinates of the points of intersection of the curve and the straight line y equals x minus 1. So I know that this is going to happen when theta equals pi by 2. And when theta equals pi by 2, the coordinates, the x coordinate is sine theta, the y coordinate is cos squared theta, well, sine theta is 1, and at that same point, cos would be 0. So there's only one point of intersection, which is 1, 0. Okay, so I'm going to stop that there, because otherwise this is going to be a huge recording, and I'll upload these separately. And I'll go and see what my answers to the original one were. Oh, why can't I stop it?